So we have been looking at problem of solving ordinary differential equations subject to boundary conditions using method of orthogonal collocations. So this is based on using interpolating polynomial, and this interpolating polynomial is used over the domain of interest, and this interpolating polynomial is then used to discretize the problem, discretize the boundary value problem. So let's look at a quick recap of what we have achieved till now. I have been looking at this problem of a general second order boundary value problem, which is dz square psi is a general function, du by dz, u and z is equal to 0. Now this holds, this equation is supposed to hold over domain 0, z less than 1. So here u is some dependent variable. It could be temperature, it could be concentration, whatever is temperature, whatever is the variable of interest. So we have this generic second order ordinary differential equation, and then I have two boundary conditions at two boundaries. So these are f1 so this is my boundary condition 1, and then my second boundary condition is du by dz So I have this generic problem of solving second order ordinary differential equation subject to these two boundary conditions, one at z equal to 0, the other one at z equal to 1. Okay, so if I draw this on this domain, we have this domain here, and we have already set the convention of naming. So we have this domain here, this is z equal to 0 to z equal to 1. Okay, and then we have a solution, we have a polynomial solution, interpolating polynomial solution, which we have assumed. So this is uz is equal to alpha 0 plus alpha 1 z plus alpha 2 z square plus alpha n z to the power n. This is the interpolating polynomial, which is the proposed approximate solution. And we had this convention of deciding or calling solution at certain points, which are called as collocation points or the grid points. So in this context, we are going to call them as collocation points. So we have these collocation points which are numbered, z1, z2, z3. In general, this is zi, this is zi plus 1, this is zi minus 1, and the final one is the final point is called as zn plus 1. So we have this n plus 1 collocation points numbered from z1, z2, z3 up to zn plus 1. So these are collocation points. Okay. Now these collocation points need not be equispaced. Okay. We have looked at finite difference method. In finite difference method, we looked at two options. One was the grid points, as they were called in the finite difference method. The grid points could be equispaced, they could be non-equispaced. In this case, though in principle no one stops you from taking equispaced points, we are going to look at these collocation points chosen in a particular way. These collocation points are going to be chosen at the roots of shifted de Genere polynomials. Okay, so these are going to be these collocation points are going to be chosen at the roots of shifted Legendre polynomial are given in the lecture notes. So I'll just list them here. So for example, okay, if I take the first order polynomial, then so first order polynomial, then the root is at 0.5. Okay, if I take the second order polynomial, then the root is at 0.21132 and 0.78868. If I take third order polynomial, then I have three roots, 0.1127, 0.5 and 0.8873 and so on. So if you look at the standard textbooks, you will get these roots of the shifted Legendre polynomials, and I'm going to place these collocation points. Okay, at the roots of this shifted Legendre polynomial, which means if I happen to choose three collocation points in this domain, okay, the first one of course z1 will be 0, the second one will be placed at 0.1127. okay, this is scaled, this domain is scaled between 0 to 1. Typically if it is length, you can divide by length and scale it to 0 to 1. So at 0.1127 will be my second point, my third point will be at 0.5, my fourth point will be at 0.8873, and by the last point, the fifth point, will be boundary z equal to 1. Okay, so likewise in here in the accompanying notes, I have listed roots up to 7th order. Okay, and you will get, if you want to know about higher order polynomials, you will get that in the literature. So this, but typically it suffices to use 3rd, 4th, 5th or 6th order polynomials. And if you want to have more collocation points, then typically what we do is we do orthogonal collocation on finite elements, which means we divide it into sub-elements, and within that element we define collocation points. Okay, so we don't really go for, if we want 50 collocation points, we don't do it by taking the 50th order polynomial. We take a 5th order polynomial, divide this domain into 10 segments and place roots inside each subdomain. Okay, but that we will not be discussing now. We'll be looking more at a single polynomial being chosen at. Okay, so let's do a quick recap of what we have done till now. Well, we want to find the solution, approximate solution, and then this approximate solution, I have a naming scheme. So my u1 corresponds to u, that is this approximate solution computed at z1, okay, and u2 is u computed at z2 at the second collocation point, okay, and so on. So in general, ui corresponds to u at z equal to zi, okay. Now what we said in the last lecture is that we would like to express these coefficients alpha 0, alpha 1, alpha 2, alpha n. Okay, these are unknowns. Okay, this is a proposed approximate solution for this ordinary differential equation. Okay, and these coefficients I want to express in terms of u1, u2, u3, u4 and so on. Okay, so what is known to me here? What is known to me here is I have chosen the collocation point. So the collocation points are known to me. Okay, so these locations, that is z0 or z1 equal to 0 to z2. Let's say if you take 3 points, z2 equal to 0.1127. These locations are known to me. Okay. Now what we have done in the last lecture is like this. Okay, to get unknowns transformed from alpha 0 to alpha n. Okay, we wrote this equation at n plus 1 collocation points. So I wrote this equation u1, u2 up to un plus 1. So un plus 1 is at the last point. Okay, then this will be 1 z1 square up to z1 raised to n, 1 z2 square up to z2 raised to n, and so on. Okay, and we have this 1 zn plus 1 alpha 0, alpha 1 up to alpha n. Okay, I wrote it in this form. This is I defined this matrix as A matrix, if you recall. I call this as vector theta, and these are my unknowns. These were represented as capital U. Okay, so to eliminate, to express this alpha 1, alpha 2, alpha 3, alpha 4 in terms of unknowns u1, u2, u3, u4, well, the problem here is that u1, u2, u3, u4 are actually solutions of this ordinary differential equation, okay, at the collocation points. So this u1, u2, u3, u4 are not known to us. They will be known to us when we solve the differential equation. Okay, so here there is a trouble. We do not know u1 to un plus 1. We do not know alpha 0 to alpha n. But we want to transform the problems from these as unknowns to these as unknowns. Okay, so the way it has been done is to write this equation u is equal to a theta. Okay, this implies that theta is equal to a inverse u. Okay, theta is equal to a inverse u. Next, what we have done is we need derivatives of this function to be evaluated. See, because here in this equation you have d2u by dz square, you have du by dz. So I need these two equations to be evaluated, right? So for this, what I have done is, so in the last class I derived this expression. Just to recall, I will not derive it again. I just write the expression. Okay, so we said that we wrote this as 1 z to the power n into theta. We wrote this as inner product of two vectors. One vector is 1 to zn, okay, and times theta. What is theta vector? This is theta vector. Okay, this is theta vector. And then we said that this is nothing but 1 z to the power n into a inverse u. Theta was replaced by a inverse u. Okay, so instead of unknown as theta, we have now unknown as u. Okay, and then I wanted du by dz. Okay, I wanted du by dz. If you take du by dz, this vector becomes 0, 1 up to n z to the power n minus 1 a inverse u, right? This vector is just 0 to, yeah, and then I want to evaluate the derivative. I want to evaluate the derivative at these collocation points. So if I want to evaluate the derivative at the collocation points, this becomes, so du by dz at z equal to zi. Okay, this is equal to 0, 1, n Zi raised to n minus 1 A inverse U. Okay, so this is the expression that we derived for the first derivative. Okay, similarly, we derived the expression for the second derivative. Okay, we derived the expression for the second derivative. What is this expression? So I call this, okay, before I move to the second derivative, this vector, okay, I call this vector as Si. I call this vector as Si transpose. Okay, this Si transpose, okay, was defined as 0, 1, this matrix, this A matrix is known to us. Okay, this A matrix is known to us. So A inverse is known to us. A matrix can be computed using, since we know Z1, Z2, Z3, we can compute A matrix, we can compute A inverse. Okay, so this matrix is known. Since we know Zi, we also know this row. Okay, so this row times this matrix, this will be a row vector. That row vector I am calling it as, okay, Si transpose. So my D okay, my equation assumes the form du by dz equal to Si transpose u. Okay, so likewise I also derived expression for the second derivative d2u by dzi, okay, dz square, okay, and that turned out to be, I'll just give the final expression because we have done it last time. So it turned out to be 0, 0, 2, okay, we derived a generic expression for the second derivative. Okay, just look here. This is the first derivative. If I differentiate this with respect to z again, you will get 0, 0, n minus 1 will come here. Okay, this is just differentiation of this. This is a constant matrix. So this expression naturally follows from this, and this is what we got. We decided to call this particular vector as Ti. I decided to call this particular vector as Ti transpose into U. Okay, so which means I have an expression that is d2u at zi dz square is equal to Ti transpose into U. Okay, I have expression. So what have I achieved? What I have done is I have expressed the derivative at a particular point at z equal to zi, okay, as a vector times unknowns. What are the unknowns? Unknowns are values the dependent variable takes at the collocation points u1, u2, u3, u4. Okay, so this is the derivative at this point is some linear combination of this vector u1 to, okay. See what is the difference here. So when are u1 to u2 and u3 defined? So this is u1, this is u2, this is u3 and so on. So this is ui plus 1. So this will be so this is Zn, so this is Un, this will be Un minus 1 and so on. Okay, so what is my U vector? My U vector consists of this dependent variable values at 0.1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is entire vector is that u vector. Okay, see what has happened. When you do finite difference, okay, you express the local derivative using only neighboring points, or you express the second derivative only using neighboring points. Whereas here the first derivative or the second derivative is a linear combination of entire, okay, u1 to un. So this is the difference. This is the main difference. Okay, everything comes into the picture. Okay, so this is much better way of finding the derivative than taking a local derivative. Okay, and then this now we are going to use to formulate the problem. Okay, so last time we stopped here. Let's now actually form the the substitute these values at the grid points and come up with the equations that need to be solved to get this u1 to un plus 1. We still do not know what are the values of u1 to un plus 1. All that we have achieved till now is to express these derivatives in terms of the unknown variables. What are the unknown variables? u1, u2, u3 up to un plus 1, which are values the dependent variable takes at the collocation points. Okay? Now let's see how to solve the problem. Now I want to solve this problem. Okay, so actually, see this ordinary differential equation, where is it defined? It's defined on the domain, yeah, it's defined on the domain 0 to 1. So it should hold, where should it hold? Everywhere. Ideally, the true solution, okay, the true solution uz, okay, this is not the true solution, this is an approximate solution. The true solution should actually hold at every point in this domain. That's what it says. Okay, now when we solve it by orthogonal collocation, we are going to say that, well, the approximate solution should hold only at the collocation points. Okay, right now we are not saying anything what happens in between. At the collocation point, this equation should be satisfied. At the collocation point, this equation should be satisfied. Okay, so this is discretization. Actually we are looking at only finite number of points where the equation should hold. The original equation should hold everywhere. Okay, so what's going to happen now is, because of this approximation, this ordinary differential equation will get transformed into set of nonlinear or linear algebraic equations. Okay, then so this should hold inside the domain. At the boundary points, what should happen? This equation should hold at first boundary, this equation should hold at the second boundary. So these equations, okay, enforcing this equal to 0 at each of the collocation points will give you a set of equations, plus these two will give you two more equations. We'll have number of equations equal to number of unknowns, and then we are going to solve it. Okay, so now let's embark upon solving the problem. Okay. So the game plan is enforce so this is called residual. I'll just write down what you will understand why I'm calling it residual. To 0 at each collocation point. So that means what I'm going to do, I'm going to solve this equation. This is called residual psi. Okay. Now d2 u zi by dz square, du zi by dz, u zi, okay, or in our case u zi is nothing but ui, zi should be equal to 0. This term I am going to call as residual. I want this equation to hold at every grid point. Which are those grid points? For I equal to 2, 3 up to n. Okay, I want this to hold at, okay, now if I substitute for expressions that I have got, see the derivatives are now expressed in terms of algebraic expressions. Okay, I'm going to replace them. So this actually means I want to solve for Ti transpose U Si transpose U Ui Zi equal to 0. Look at this equation here. Okay, see du by dz square I have replaced by equivalent algebraic approximation. Okay, sorry, d2u by dz square I have replaced by appropriate algebraic approximation. Du by dz I have replaced by appropriate algebraic approximation. Okay, so this differential equation is now converted into an algebraic equation. How many such equations we have got now? We got I equal to 2, 3, 4 up to n. So how many equations? N minus 1. We got n minus 1 starting from 2 to n. We got n minus 1 equations. Okay, we are going to set this residual equal to 0 at each of the collocation points, internal collocation points. Okay, now what about boundary conditions? See, how many unknowns are there? u1, u2, u3 up to un plus 1. Okay, so how many equations you need? You need n plus 1 equations to solve, get, okay, how many equations we got till now? N minus 1. So we need 2 more equations. Those 2 equations are going to come from boundary conditions. Okay, so the boundary conditions will give you additional 2 equations that completes the set. You get n plus 1 equations in n plus 1 unknowns, and then we are solving the problem. We will solve them using okay. So let's write the 2 additional equations. Okay, so the next equation is f1. Okay, s1 transpose u1 at z equal to 0 This is my first equation. And f2 s n plus 1 transpose u un plus 1 and 1 equal to 0. Okay, see now you have these two equations, okay, and these n minus 1 equations. Okay, these n minus 1 equations together with these 2 equations forms the set of n plus 1 equations. N plus 1 equations in n plus 1 unknowns, we need to solve them simultaneously. Okay, if these happen to be linear algebraic equations, you can solve them analytically. If they happen to be non-linear algebraic equations, you have to solve them iteratively using some iterative method. Okay, so what we have done here, we have achieved transformation of the problem, of a boundary value problem, okay, from a differential equation to a set of algebraic equations. Okay, using approximation theory. What method in approximation theory we have used? We have used interpolation, interpolating polynomial. Okay, so these equations, then you can solve it using the standard tools like Newton's method, Newton-Raphson, or successive substitutions, whatever is suitable that you can use to solve this particular problem afterwards. Okay, let's take a specific example, then it will be easier for you to understand. Before that, I just, for the sake of convenience, I want to define 2 matrices. Okay, using this S vectors and using this T vectors, I'm going to define 2 matrices S and T. Okay, I'm going to give you a method to compute them very easily. Okay, so we will define these 2 matrices, and then for a given number of collocation points, one has to first construct these matrices and then use them to formulate your equation. One thing which I would like to bring to your notice here is that in every equations, these are dense equations. These are dense equations. In every equation, okay, u1 to un plus 1 will appear. Okay, because the derivatives are approximating not locally but using all the points in the domain. Okay, since the derivatives are approximated using all the points, these equations will be dense. Okay, so this is something different from if you do finite difference. Okay, only two neighboring variables will appear in one particular equation. Here it is not like that. Every variable will appear in every equation, particularly if you take a single polynomial over the entire domain. Okay, so that is a big difference. Okay, so let me define this matrix S and T, and then we will take this particular example that we have been using quite often, or we will be using quite often in the course, which is tubular reactor with axial mixing. So, so before we do that, let me define these matrices. So this S matrix is going to be defined like this. It consists of S1 transpose, S2 transpose. So here S superscript 1 implies it's a vector. First vector, second vector, third vector, and so on. So this is going to be S n plus 1 transpose. Okay, so this is a n plus 1 cross n plus 1 vector. Okay, this is a n plus 1 cross n plus 1 vector. Okay, and it's very easy to show that this can be computed by looking at this another matrix 0 1 . So if I decide to call this matrix as say C matrix, then this is equal to C times A inverse. C times A inverse. Well, how was our A matrix defined? A matrix was defined. Just keep it in background that we had this equation that U is equal to A theta. Okay, U equal to A theta. So A matrix is defined, okay, using one Z1, Z2 and so on. So likewise I am also going to define this T matrix. I am going to define this T matrix. This T matrix will consist of okay, so I have stacked up these row vectors. Okay, to create this matrix. Okay, why this funny notation? Because in our course, whenever we are defining a vector, it's a column vector. When I want to make it row vector, I am taking a column vector and putting it as a transpose. That's why this notation, which we are getting. Okay, and then you can show that this matrix is equal to, this can be very easily computed using D times A inverse. And what is this D matrix? Okay,
this is n plus 1 cross n plus 1.
This is also n plus 1. Yes, this is also n plus 1 cross. This is also n plus 1 cross n plus 1 matrix. Yeah. So let's write this D matrix. This D matrix is slight modification of this matrix. So D matrix will look like this. D matrix will be 0, yeah, 0, 0. This will be 0, 0, 2, 6, Z1. This is n minus 2, this is n minus 2, and so on. So this is nothing but okay. So this D matrix will look of these stacked vectors. Okay, these are nothing but Ti vectors evaluated at different collocation points, and this together with A inverse post multiplied by A inverse is going to give me T matrix. Okay, so I need to create, as a preparation for solving this problem, okay, I need to create this S and T matrices, okay, by choosing collocation points. Once I choose collocation points, okay, 3, 4, 5, 6, whatever, once I choose the collocation points, I can first find out A matrix. Once I find out A matrix, I can find out A inverse, and then I can define C and D matrices, and from that I can get S and T matrices. Once I get S and T matrices, I'm going to use rows of these matrices to discretize my ordinary differential equation and convert it into algebraic equations. Let's take a specific problem that you will understand it better. Okay. Okay, so this is our tubular reactor with axial mixing. Okay, this is the problem which we have looked at earlier when we studied the finite difference method. Okay, the associated ordinary differential equation is 1 by Peclet number into d2c by dz square minus dc by dz minus dA c square is equal to 0. So this is the ordinary differential equation that should hold between 0, z, 1. Then you have two conditions. Okay, you have two conditions, that is dc by dz, okay, is equal to PE into C0 minus 1, and this should happen at z equal to 0. And dc by dz equal to 0 at dc by dz at z equal to 0 equal to 0. Okay, this is the second condition that we have. Two boundary conditions, and
second boundary condition is equal to 1.
Yeah, second boundary condition should hold at z equal to 1. The second boundary condition should hold at z equal to 1. So this is my problem. This I want to discretize. Okay, let's say I have chosen 3 internal points. Okay, so I'm going to do a very simplistic solution. So this is my Z1, this is my Z5. Okay, I have 3 collocation points. Okay, this is Z2, Z3, Z4. Okay, I have taken collocation points at the roots of the third order shifted Legendre polynomial. Okay, so these happen to be, you know. So the first one is at 0.1127, second one is at 0.5, third one is at 0.8873. Okay, this Z5 is equal to 1 and Z1 is equal to 0. So we have 5 collocation points, 3 internal collocation points, 2 boundary points. Okay, and then we are going to get 5 equations in 5 unknowns. Okay, we are going to get 5 equations in 5 unknowns. Now, what is the first thing to do here? First thing to do is to compute A matrix. Okay, first thing to do is to compute A matrix. So A matrix, okay, if I actually compute A matrix, okay, if I compute using these 5 points, it will be 5 cross 5 matrix. Okay, then if I compute S and T matrices, okay, I'll just write here a sample of S and T matrix. So S matrix, first row turns out to be minus 13, 14.79, minus 2.67, 1.88, minus 1, and so on. Okay, so this is a 5 cross 5 matrix. So there are 5 rows. This is the last row, this is the first row. Okay, likewise, knowing these points, once I have chosen these points, I can compute A matrix. Okay, then I can compute C and D matrices. Then I can compute S is equal to C into A inverse. I can compute T is equal to D into A inverse, because A, C and D, these matrices depend only on the values of the collocation points. Okay, so once I have got these matrices, okay, then I am going to use these rows of these 2 matrices to convert this differential equation into set of algebraic equations. Okay, so what is my first equation? So I have 3 equations at the 3 internal collocation points coming from this differential equation. I have 2 equations coming from boundary conditions. Okay, so my equations would look something like this. Okay, so 1 by PE into PI transpose times C vector minus SI transpose times C vector minus DACI square is equal to 0. Sorry, not here. Okay, I going from 2, 3, 4. Okay, what is the C vector? C vector now consists of C1, C2, C3, C4 and C5. Okay, C vector consists of C1, C2, C3, C4, C5. Okay, so this row times C1, C2, C3, C4, C5, okay, plus this row times C1, C2, C3, C4, C5 plus C2 square when I equal to 2. Okay, second row, here you will choose the second row from the matrices. Here when you choose I equal to 3, you will choose the third row from S and T matrices, okay, and you will get here dA into C3 square. Okay, so you are getting three nonlinear equations. You are getting three nonlinear equations, and the two additional equations arise from boundary conditions. Okay, so the two additional conditions that you get is S1 transpose C minus PE into C1 minus 1 is equal to 0, and S5 transpose C minus is equal to 0. Okay, so these three equations plus these two equations together they form 5 nonlinear algebraic equations which need to be solved simultaneously. Okay, because particularly these equations, everything appears, all the equations, C1 to C5 will appear in all the equations. Okay, these are coupled nonlinear equations. They have to be solved iteratively using Newton's method, Newton-Raphson, or some nonlinear equation solver, which maybe optimization method, whatever is at hand for you to solve this. So this is the original problem, okay, which is actually defined on a domain which is not finite dimensional. See, the true solution here, let's come back here. What is the true solution here? True solution here is the concentration profile as a function of z. Okay, z varying from 0 to 1. So it's a function. Okay, it belongs to, which set does it belong to? It belongs to the set of continuous functions, twice differentiable, defined on domain 0 to 1. The true solution is actually that. We have discretized the problem, okay, using interpolation polynomial, only converted into a fifth order, five dimensional vector. Okay, so we are approximating an infinite dimensional solution using a five dimensional vector. Well, you can increase the number of collocation points to 7, 8, 9, but you know how many you can go. So if you want to really make a higher dimensional approximation, what one could do is one could divide this into segments, and on each segment one can define a lower order collocation polynomial. Okay, then of course that is called as orthogonal collocation on finite elements. Then you have to write conditions by which the neighboring solutions are meet each other. So those conditions will have to be written. Okay, additional conditions will come out of that. To maintain the continuity of the solution, you will need additional conditions to be imposed. Okay, but this is the basic principle. Once you understand this, extending it to finite element is not difficult. This concept is this. Okay, now before we close this lecture, I also want to show that this is not just converting the boundary value problem. I am going to just take a version of the same problem, which is a partial differential equation. Okay, and then you will see that the partial differential equation, okay, will get converted into an ordinary differential equation, set of ordinary differential equations. Here, there is no time involved here. Okay, I am going to now convert this into a partial differential equation by including the time derivative. If I include the time derivative, the same problem, okay, instead of getting transformed into set of coupled algebraic equations, nonlinear algebraic equations, it will get transformed into set of coupled ordinary differential equations. Okay, then of course you have to use methods to solve the ordinary differential equations. That is a separate thing. Okay, right now we are just looking at the problem transformations. Okay, so let's do a quick recap. What we have done is we have this second order ordinary differential equation. Okay, we have proposed a polynomial interpolation based solution, approximate solution for this dependent variable in terms of independent variable z. Okay, nth order polynomial interpolation polynomial, and then we are forcing this residual, we call this as a residual, to be 0 at a finite number of collocation points. These collocation points are chosen at roots of the shifted Legendre polynomial. Okay, why shifted Legendre polynomial? Why not why not at some say regular intervals and so on? It has been found that if you actually place them at the shifted Legendre polynomial, then the approximation errors are low. Okay, so the reason for choosing orthonormal or orthogonal polynomial, roots of the orthogonal polynomial, is to get less approximation errors. Okay, so there is a reason why we choose the collocation points in a special way and not equispaced and so on. So let's not get into that part, but just accept this now that if you put them at special locations, then the approximation errors are low. Okay, so then we looked at one problem, which is tubular reactor with axial mixing, and this problem, what has happened is we are able to convert this particular problem into set of 5 coupled nonlinear algebraic equations, which need to be solved iteratively further. Okay, which will give you an approximate solution. Okay, now here, because the derivative approximation is much better. Okay, a derivative approximation is much better. Typically, it is found that a good solution can be obtained using less number of collocation points. So till now we have looked at finite difference method. Okay, in a finite difference method, you need large number of collocation points. You need large number of grid points to get a good solution, because you are taking local approximation of the derivative. Okay, we are taking local approximation of derivative. So you need large number of grid points to get a good solution. So what is the meaning of large number of grid points? Large number of grid points means, see, suppose you were to enforce this equation at this residual to be equal to 0 at large number of grid points, the number of equations that you need to solve simultaneously will be large. Suppose to get a good solution using finite difference, I need to subdivide this into 100 small intervals. So then here when you transform this into algebraic equations, you get 100 algebraic equations plus 2 algebraic equations at the boundary, so 102 algebraic equations. Okay, what is found here is that with this approximation, less number of collocation points, a smaller order polynomial, gives you a good solution in many cases. Okay, so here using this method, you can get good approximations using less computations in some sense. Okay, so just to compare, okay, let me before we just close the lecture, let's just look at the partial differential equation and then let's see what happens. Now I'm going to keep the same problem. Okay, I'm not going to change the problem, except in this case I looked at the steady state solution. I did not consider time. But suppose you were to consider the transient response of the tubular reactor with axial mixing. Let's keep the same problem. Okay, so I'm going to say here dou C by dou T is equal to, so these become partial derivatives, dou 2C by dou Z square, dou C by dou Z into, so the time derivatives earlier we had put it equal to 0, now the time derivative is not equal to 0. So now my second example, that is, this is PDE. Okay, so I want these conditions to hold at all time. So I want this condition to hold at all the times. So dCt by dZ, okay, is equal to Okay, now the time has come into picture. Okay, and I want the solution to obey these. I want the solution to obey these equations at all the times. Okay, at all the times. So this is Ct. So now there are two attributes to the solution: time and space. There are two attributes to the solution. This is a partial differential equation. Earlier we were looking at a boundary value problem. There was only one attribute, that is one independent variable, that was space. Now my solution will be time and space. Okay. So when I convert this problem, when I discretize this problem, I am going to only consider discretization in space. I am not going to right now discretize in time. I am going to keep time intact. Okay, and discretize only the right hand side, the spatial part. Okay. So what happens if I so at the internal collocation points, I get three differential equations. What are those three differential equations? Now there are three differential equations in time. Okay, the right hand side becomes algebraic. Okay, because these derivatives are approximated using method of collocations. Okay, this we don't approximate. Okay, right now. So we have this equation which is written at the three internal grid points. Okay, dci by dt, okay, is equal to 1 by Peclet number into Ti transpose C. So here now of course Ct minus Si transpose Ct minus dA Cit square. Okay, I going from 2, 3 and 4. Okay, I going from 2, 3, 4. Okay, and then this last two equations becomes two algebraic constraints. So what you get is set of differential algebraic system. Okay, what you get now, because these are spatial derivatives. This is a time derivative. Okay, the spatial derivatives will get converted into algebraic equations. Okay, so there are algebraic constraints to be obeyed at the boundary points. Okay, and this partial differential equation gets converted into ordinary differential equation. Okay, so we have three ordinary differential equations, and there are two algebraic constraints at the boundary, that is S1 transpose Ct equal to okay. So there are three differential equations. These are three coupled nonlinear differential equations, and they are coupled tightly with these two algebraic constraints, and they have to be solved simultaneously. You can see here, what is this Ct vector? Ct vector is C1t, C2t, C3t, C4t and C5t. Okay, so dC2 by dt, dC3 by dt, dC4 by dt, all of them are functions of C1, C2, C3, C4, C5. Not only that, because of this square coming here, these are nonlinear functions. Okay, so there are three nonlinear differential equations, two algebraic equations coupled. Okay, in this case you may be able to eliminate two variables. Let's say you decide to eliminate the first and the last. Okay, you decide to eliminate C1 and C5. It may be possible because these two are linear constraints. Okay, there is no nonlinearity here. So you might be able to rearrange and express, okay, C2, you might be able to express C1 and C5 in terms of C2, C3, C4. If you do that, then you can eliminate here, and then you will get 3 differential equations in 3 unknowns, and then you can solve them by whatever method. But then that is one way, or you solve them simultaneously using a method for solving differential algebraic systems. Okay, so this is how you transform a problem which is originally a ordinary differential equation boundary value problem, okay, into set of algebraic equations, linear or non-linear. Okay, if it happens to be a partial differential equation, you will get a set of ordinary differential equations plus algebraic conditions. These have to be solved simultaneously, and then you arrive at the solution. Okay. So what we have learned in this part is that how interpolation polynomials can be used to transform a problem. Okay. So we began by see what is the foundation of all this. The foundation is that why we could construct a polynomial solution, because some time back I talked about Weierstrass theorem. What does Weierstrass theorem tell you? Weierstrass theorem tells you that any continuous function can be approximated arbitrarily by using a suitable order polynomial. Okay, that's why we could construct a polynomial approximation to the solution CZ or CTZ. Okay, that's why we could construct a polynomial approximation. Okay, now using that polynomial approximation, how do you construct a polynomial approximation? Weierstrass theorem only tells you that there exists a polynomial approximation. Here, you actually can, you have to actually construct it. The first method that we saw was Taylor-Series approximation. Okay, that led to finite difference method. The second method that we saw was interpolation, that has given rise to orthogonal collocations. Okay, in the next class onwards, we will start looking at least squares method. So least square fitting. Okay, and then in the context of least square fitting is a very vast area, and I'll be talking not just about converting boundary value problems or partial differential equations. I'll be talking about many more things under least squares. Now, in the context of partial differential equations or boundary value problems, we'll get the method of finite element, the so-called method of finite element. Okay. So with this, we'll close this lecture and move on to least squares methods in the next class.